as we have introduced the exercise showing here, and this is slide just to highlight how can we do the dimensional analysis by step-by-step methods. And then for this exercise, the number of the physical parameters is 5, and the number of the dimensional is 3. So actually for this problem, we will have the two pi groups, and based on this dimensional analysis, finally we know that the false coefficient is a function of Reynolds numbers. So the slide just summarize the result in here. So the pi 1 is, we call that the back coefficients, and the pi 2 is indicate to the Reynolds numbers. So, but one problem rising here is because for the last slide, to the dimensional analysis, we cancel out the d-dimensionals by the velocity divided the diameter here. But right now, if we use this parameter to delete the dimensionals for other two parameters, we will have a different pi 1 result. So that means if we use the different item to cancel out the different dimensions, we will have a different result of the pi groups. So actually, the form of any pi group can be altered by multiplying or dividing by another pi group. So if we use the pi 1, multiply the pi 2 and the square, and then we will have another pi 1s. This is the pi 1, we call that the back force coefficients. So no matter you use the different parameter to cancel out the different dimensions, actually the pi 1, pi 2 can combine together to have another pi 1s. Okay, so the next we would like to introduce another method to do the dimensional analysis, which is the exponent methods. So this method involves solving a set of the algebraic equations to satisfy the dimensional homogeneities. So this is the table summarize the exponent method step by step, but we just use one exercise to see what happens for the exponent methods. So again, the exercise, the problem is the drag force Fd of a sphere in a fluid volume as the sphere is a function of the viscosity mu, the mass density rho, the velocity of flow v, and the diameter of the sphere d. So use the sorry, here is the use the exponent methods to find the pi groups. So again, we just exercise tell us the drag force is a function of the velocity, density, viscosity, and the diameters. So we list the 1, 2, 3, 4, 5. So totally we have the 5 numbers of the physical parameters, and we just show the dimension for each parameters. So this is a mass L divided p squared, L divided T, N divided L cubic, N divided LT, and the diameter is L. So the left-hand side, we know the dimensional is for the drag force, it's NL divided T squared, and this is the velocity, density, viscosity, and the diameters. So we didn't know actually the certain values for the power, so we used the A, B, C, D. So we just reorganize all of the power coefficients. So and we just make the balance left hand side and right hand side. So we know that the L is A minus 3B minus C plus D equal to 1. And the B plus C is equal to 1 also. And the A plus C is equal to 2. So we have the three equations, but there are four unknown parameters. So we just uh, solve these equations, and then we know that the A is directly to equal to D, D equal to D also D minus 1, C is equal to 2 minus D. And then we put the coefficient A, B, C back to the equation shown here, and we just rearrange the coefficients, power coefficients, and then finally we know that the rho F divided the mu squared is equal to rho V D divided the mu with the D powers. So actually, after the dimensional analysis, we only know that the rho F divided the mu squared is a function of the Reynolds number, but we didn't know what the numbers in here. So we need to conduct the laboratory experiments to investigate the relationship between the Reynolds number and the rho F mu squared here. So as we know, we can compute the drag force from the dividing pi 1 by the square of the pi 2. So previous study already conduct a series of laboratory experiments and figure out the relationship between the drag force CD and as a function of relationship between the drag force CD and the Reynolds numbers. They also find out the drag force coefficient is not only as a function of the Reynolds numbers, but also the roughness here. So you see the different roughness will have a different trend between the CD and the Reynolds numbers. So we know actually that if the the severe surface is a relatively higher roughness, and then the drag force is not responding to the Reynolds number changes. So this is a very important result. So there are the exercise, the true data, and can be helpful to better understand the relationship between the drag force and the Reynolds numbers. So the experiments will carry out in the water tunnels and the wind tunnel to measure the drag force on an object. The water tunnel was operated with the fresh water at the 20 degrees, and the wind tunnel was operated at the 20 degree also, and at atmosphere pressures. Three models were used with the dimensions of the 5, 8, and 15 centimeters. The drag force on each model was measured at a different velocity. Okay, so the following data was obtained. So the table just summarizes data from the water tunnels and the wind tunnels. And we know that the model size is different and ranges from the 5, 8 to 15. And we also conduct different velocities, okay, and also the different force. So we just based on those parameters to compute the pi1 and the pi2 values for each data, and then we draw the scatter plot. So the y-axis is the force coefficients, and the x-axis is the real numbers. Different label numbers indicate the data are from the different uh, conditions. The one is from the water tunnels, the two is from the wind tunnels, and we do a regression analysis. Finally, we find out the coefficient B in here is the minus 0.307, and we find out the constant values of the A is 1.355. Okay, so that we can see if the real numbers ranging from around these values, and then we see that the real number increase and the drag force coefficient decrease a lot. So based on the dimensional analysis, we only know that the force coefficient is as functions of the real numbers. So we didn't know actually the certainty coefficients and a certain relationship between the real number and the force coefficients. But we have the experimental data, and then we know that actually the relationship between the force coefficients and the real numbers. So this is very important. If we know that the certain relationship between two pi groups, then we can conduct the experimentals to understand the certain relationship. And then, so that one thing is very important, which is the selections of the significant variables. So to apply the dimensional analysis, one must first decide which the variables are significant. So you can use the more physical parameters to do the dimensional analysis. After the analysis, finally you only have the pi groups related to your physical phenomena. So this is very important. You need to do the selections of the significant variables. So the slide just showing here, I would like to introduce the common pi groups for our hydraulic problems. So there are the primary dimensionals of the significant independent variables, such as the velocities, densities, viscosities, gravities, the surface tensions, and the Mach modules, and the diameters. So totally there are the 7 primary dimensions, and we call that are the significant independent variables. So you can see the surface tension is very important for the conditions under a liquid-gas interface. And the bulk modules is important that because of the definitions of the fluid compressibility. And this is very important parameters for the diameter of a pipe. And the gravity can control the body force from the gravity force. And the viscosity is a good parameter to better understand the viscosity effect. We have a density and also the velocity. And then there are the three dependent variables. The first one is the pressures. This is the pressure in the hydraulic we call that the pressure is a normal stress. And we have the shear stress from the viscosity effect. And we have also the surface tension force, which is from the surface tension problems when our condition is on the liquid to gas interface. So totally we have the three dependent variables. So the previous slide just showed out the 7 independent variables, and here we have additional 3 dependent variables. So totally we have 10 important variables. And if you take a look at the dimension of the 10 variables, we only have the 3 basic dimensions such as the mass, length, and the time. So we will result the 7 pi groups. So the following slide just introduce the 7 pi groups and their physical meanings of the variables. So first we show up the 3 dependent pi groups. The first one is we call that the pressure coefficient. Second, we call that is the shear stress coefficient. And the final one is the force coefficient. And we use the different names CP, CF, and capital CF. You can see the pressure coefficient is defined by the pressure difference divided the kinetic pressures. And this is very useful to do the cavitation analysis. And the second is the shear stress coefficients. We have the shear stress here, and then the bottom is also the kinetic pressures. And usually we use this parameter to study the friction effect for our problems. And the final one is the force coefficients we have introduced previous slides. And so we actually know that this is the force and also divided the kinetic pressures. And the force can be the back force or the lift force. So in our previous slide, the exercise just use the force the back force at B. So there are the 3 dependent pi groups we introduced already. So we have additional 4 independent pi groups. The first one we call that the Reynolds numbers. Right now you are well known the Reynolds numbers, and the following 3 variables you didn't know before. The first one we call that is the Mach numbers, and And the sequence here is the Weber numbers, and the final one is the Froude numbers. So what is the physical importance for the following four independent pi groups? And I will introduce individually in the following slides. So each independent pi group has an important physical interpretations as indicated by the ratios column. So what are the meanings? If we look the Reynolds numbers can be viewed as the ratios of kinetic to viscous force. As we know, so we first define the ratios between the kinetic and the viscous force. And the kinetic pressure, we know that is proportional to the rho v squared. And this is actually the pressure unit, and we would like to convert it to the force. So we have additional dimensions is the L squared is related to the areas. The pressures multiply the area dimensions, so the unit transfer to from the pressure to the force. So as you see here, the uppers we have a low v squared and the rho squared, and the bottom is related to the viscous force. So the viscous force we have the shear stress tau, and we also multiply the areas. The unit dimension is L squared. So this is the ratios is a rho v squared divided the tau. And we know that the shear stress is proportional to the mu viscosity multiplied the velocity gradients. So we know the upper is the velocity and the bottom is the length. And there's the mu. So we put here, we put this to here. So we know that the rho v squared and the tau can be replaced by the mu v divided L. So finally we can cancel out the v one times, so the upper only have the v, and there is divided L to move the uppers, and the bottom only have the viscosity properties. So you see, after we make the balances, so finally we know that the kinetic force divided the viscosity force, the ratio is directly equal to the Reynolds numbers shown here. So usually the Reynolds number will be used if your problem includes the viscosity effect. And then the Mach number is an indicator of how important compressibility effects are in a fluid flow. And we know that propose a certain threshold is 0.3. If your Mach number is less than 0.3, that means your problem is not affected by the compressibility effects. So the equation showing here is a certain definition of the Mach numbers, m is directly equal to the velocity divided the sonic speed. And here we know that the sonic speed is equal to the root of the ratio between the Mach modulus and the density. So you see that under the temperature of the 20 degrees, the sonic speed in water is the 1480 meter per second, and the sonic speed in air is the 340 meter per second. So if our flow velocity is less than the 440 meter per second, or the air speed is less than 1000 meters squared, and then we will have the Mach number is less than 0.3. So our fluid problem is satisfied in compressible conditions. So those two parameters are very important when you meet the problem and you need to identify the problem involve the compressibility effect or not. So please remember and keep in mind two numbers. So here for the flow velocity is the 440 meter per second and the airspeed is the 100 meter per second. So usually the Mach numbers is larger than 1. We call that the condition is a supersonic flow, but it is not normal situations for our civil engineering problems. And the third parameters is the Weber numbers. So as you see, the definitions of the Weber numbers is kinetic force divided surface tension force. So if the Weber number is small, uh, your problem will involve the surface tension force, and you need to take into account for the surface tension force. And the final one is the full numbers. The full number is defined by the ratio between the velocity and the root of the gravity L. So that's a very normal variables be used in the open channel problems. So if you see the diameter, if the diameter L, the length of L is indicate the water depth. So the larger water depth will have uh, a small flow numbers, and the small water depth L can have the higher flow numbers. And if the flow speed is large, and then the flow number is also increased. And you see this is flow number is certain defined by the ratio between the kinetic force and the gravity force. So if your problem involve the gravity effect, so you need to use the flow number to do some discussions. So the table just summarize the three dependent pi groups and the four independent pi groups. So and we know that if your problem include the viscous effect, so you need to use the narrow number. And if your problem involve the compressibility effect, and then you need to use the Mach number to solve your problems. And the Weber number is very useful if your problem involve the effect of the surface tension force. So the surface tension force usually is involved in the liquid to gas interface. And the final one is the flow numbers. The flow numbers will be used if your problem considerate the gravity effect, and then you need to define the Froude number. So after we introduce the 7 pi groups, usually be used in the hydraulic problems, and the slide showing here, we just tell you the similitude is the series and the art of the predicting what? Predicting the prototype performance from the model observations. So I just list 4 topics. They are very important. The first one is the spillways of large dams and the analysis of the sediment movement in the rivers. And the third is predict the wind loads on the buildings. And the final one is the stability characteristics of the buildings. So there are 4 topics related to the hydraulic problems, but usually we cannot directly observe from the field, and it is also very difficult to 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 understand fully based on the field survey. So we need to conduct the model testing to predict the physical behavior of the prototype phenomena. So there are 3 similitude we need to satisfy before, and then we can predict the prototype behaviors based on the model observation result. So the first one is geometric, the second is kinematic, and then the final one is dynamic. So, and in our following chapters, I only focus on the first one and the third one. That's because if you satisfy the geometric and the dynamic similitude already is, and this is naturally to satisfy the kinematic similitude. Okay, so this is a slide just show what the geometrical similitude. So you know this is upper is your prototype, and the bottom one is the model, and then we use the lower characters P means this is the prototype. And we use the M indicate this is the model. And what is how to satisfy the geometric similitude? As you can see, we just keep the ratios between the model and the prototype for the length. We need to keep the ratios. And then we have the following area ratios, and the volume ratio is directly proportional to the LR in years. So here we just keep the length ratios between the prototype and the model, and then we can easily to satisfy the geometric similitude problems. And the dynamic similitude means that the force that act on the corresponding mass in the models and the prototype are in the same ratios. We need to keep the force in model and the force in prototype to be the constant values throughout the entire flow field. So what are the meanings? The meanings, if we do that, it may not be possible or necessary to have all the independent pi groups the same for the model and the prototype to carry out the useful model studies. So it's depend on different studies, different purpose. We need to satisfy the uh, different pi groups for the dynamic similitude. So here just highlight one problem we always meet is the piping flow, and we assume the pipe is the horizontal pipe. So we can discuss the following points. The first one is the fluid fills the pipe, so there is no free surface. So if there is no free surface, we don't need to have the surface tension effect, and so we don't need to consider the wave numbers. And we assume that the problem, the compressibility effect, would not be important. So we don't need to have the Mach numbers involved in these problems. And this is the horizontal pipe, so the gravity will not be responsible for the flow. So we don't need to consider the full numbers. So the only significant pipe groups would be the Reynolds numbers for the horizontal piping systems, and the dynamic similitude would be achieved by matching the Reynolds numbers between the model and the prototype. So what's the meanings? So this is one of the exercise we would like to introduce how to use the Reynolds numbers to satisfy the dynamic similitude, or how to use the Froude numbers to satisfy the dynamic similitude. Okay, so this is the problem involve the flow over a spillway. So the gravity is responsible for the motion of the fluid. So this problem will involve the Froude numbers effect, and the second, the action of the viscous stress to the spillway surface could possibly affect the flow patterns. So the Reynolds numbers need to take into account in our problems. So if you go back to 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 go back to follow the certain definition for the dynamic similitude, we need to fix the ratios of the force between the model and the prototype. So for first, we consider the gravity. So we know that the gravity force, we for the model we use the FGM, and the gravity force for the prototype, and we actually know that the force equal to the mass multiply the acceleration. So we assume the force is computed from the gamma multiply the volumes. So here we can rewrite the force by the gamma is the specific gravity is multiplied the volumes. The dimension is L cubic, and the equal to the density multiplied the volumes to be the mass here. This is the mass, and we know that the acceleration can be computed from the velocity divided the time intervals, and we just rearrange the equation balance, and then we have a left hand side. The upper is a low GL for the model, and the bottom is a low GL cubic for the prototype, and the right hand side is the low L cubic and the velocity divided the time intervals. So we can cancel out some parameters. The first one, the density, would be the same if we have the same temperatures and the pressures. And usually for the water fluid, uh, we assume the flow is incompressible. And then you see there are the same parameters on the left hand side and right hand side. So we directly cancel out. So finally we rearrange. The left hand side is all of the parameter in the models, and the right hand side is the parameter in the prototype. And we also know that the Tm divided the Tp is equal to the ratios between the Ln divided Vn and the Lp divided the Vp. So we rearrange the equation and finally we can result the final balance equation. And if you take a look, this parameter is similar, is totally the same as with the Froude numbers. So based on the certain definitions, the force ratios, and finally we can result the force numbers. So for this problem, we need to satisfy the condition the force numbers will be equal between the model and the prototype for our problems. So as mentioned on the previous slide, we also need to consider the Reynolds numbers between the model and the prototype. So again, because we involve the nano viscosity effect in our problems, so the viscous force is very important, and we know that the shear stress is equal to the mu divided by the velocity gradients, multiply the velocity gradients, and if we multiply the shear stress by the acting areas, and then we can rewrite this is proportional to the mu v divided L multiply the L squared, and this is equal to the mu v L. So we just make the balance. We know that this is the force equal to the low the mu m bm lm divided to the viscosity force in the prototype is the mu p bp P is equal to, again we have the mass, so this rho ln cubic, and the am is the vm divided the tm, and the bottom is the same. This is rho p multiply the lp cubic and the v e divided the tp. Okay, so we just make some rearrange the equation. So first we cancel out the parameters is the Vm and the Vp, and so we have the Vn here, we have the Vp here, and we cancel out the Ln and the Lp. So there's a power to change it to the 2, and we assume this is the incompressible flow, so the density didn't change for the waters. So we just rearrange the equation balance. So we know that this is mu m divided by mu b is equal to the Lm squared divided the Tm, and this is Lp squared divided the Tp. So we just move the parameters. Okay, so this is you just put the Lp squared. We know that the Tm is equal to the Lm divided the Vm, and the Tp is equal to the Lp divided the Vp. So we know that the mu m and the mu p is equal to the Lp multiply the VP, and this is the bottom is the upper is Lm multiply the Vm, and the bottom is the Lp multiply the Vp, and then we can put all of the same prototype parameter together and the model parameter together. So we have the LP VP divided the mu P equal to the Ln Vn divided the mu M. And if we multiply the left hand side and right hand side with the density low P and the low M, and we know actually that the parameter is equal to the Reynolds numbers. So that's why we can tell you for this problem, if we start from the force ratio for the discussed event, and then finally we can have a relationship for the Reynolds numbers. And the Reynolds numbers between the model and the prototype need to keep the same. So for the spillway problems, we need to satisfy the dynamic similitude with the real numbers would be the same between the model and the prototype, and the Froude numbers also need to keep the same ratios between the prototype and the models. Okay, so let's write what are the physical meanings. The physical meaning for the dynamic similitude is we need to satisfy the force ratios for the model and the prototype. And based on your problems, you need to consider which pi groups are important for your problems. So, for example, in the spillway problems, the pi groups are important for the Reynolds numbers and the Froude numbers. And the Reynolds numbers is considering the discussed event, and the Froude numbers is focused on the problem involve the gravity force. So if actually we know that if the independent pi groups are the same for the model and the prototype, and then the dependent pi groups must also be equal. So this is based on the equation shown here. So there are the independent pi groups and there are the dependent pi groups. If we keep the same independent pi groups for the model and the prototype, and then we can say that the dependent pi groups also is equal. Because previous slide we introduced the dynamic similitude if we satisfy the force ratio the same, and then we will have the result tell us the Reynolds number and the Froude number to be the same, to be the equals for the spillway problems. So to have the complete the similitudes between the model and the prototype, it is necessary to have both the metric and the dynamic similitude. Okay, so this is very important. And so we may have a 10 minutes break, and after the 10 minutes break, we back to class, and I will show some exercise to tell you how to use the similitude analysis, and how can we satisfy the similitude, and we will focus on the dynamic similitude problems for several conditions. Okay, so I start here.